Good morning. This is Mark Richardson with Vibrant Technology, Marketing Manager, not to be confused with Mark Sr., who is the President and CEO of Vibrant Technology. So want to clarify that right up front. I'm the younger Mark Richardson. Today, we are glad that you're joining us. We are doing another webinar in our MEscope ODS video series, and today we're going to take a look at some of the unique tools that are used to process and visualize the ODS videos. And again, I'm joined by Dan Amber, Diagnostics, and
your microphone's cutting out, Mark. Hello? If anybody's listening, this is Dan Ambre. I'm going to go ahead and go. I think Mark's microphone cut out and I can't hear him. We'll just go ahead and go. So this is a look inside the MEscope Toolbox. There's a lot of different tools that we're going to be talking about. There's a couple of examples and a few new hotkeys that we've put in. A hotkey is a program that's under development. So we put it in as a separate little program, and we get all the bugs out of it, and then we put it into the software hardwired in. So we're getting close with these two, or there's 5 or 6 things we put in recently, and they're going to go in the software hardwired next week, I believe. A couple of things that we're going to talk about today: the time domain ODS animation, and it's essential for seeing motions of a shaft or blades or what have you. We also have frequency domain ODS animation, and this is does not include the shaft motions. This one will hold it in place. One of the examples today in the time waveform shows you a distortion in the rotating shaft, and it was caused by a reflective tape on the shaft, and you'll see what that looks like. I left it in because it's something that you'll probably run into, and I want to make sure you understand where it's coming from and how to get rid of it. There's some new ODSFRF formats. So the nice thing about this is the ODS format that you use for traditional operating deflection shape, and it's in an FRF, so it goes through and there's a cross power spectrum calculation that gives you the phase and the amplitude, and everything's in a format that's typical for the ODS crowd out there. There's of course color contour and vector overlays. If you've seen one of these seminars, you've seen that before. It helps you visualize the response of whatever structure or machine you're looking at. There's some live cursor hotkeys that we'll talk about, where you get magnitude and phase, you get orbits, and you initiate something called peak extraction, where you can go into the FFT, you can pull out a frequency and then invert it back, inverse FFT it back into the time domain. So you can isolate frequencies from the time domain ODS animation. So Wizards hotkeys, little new looks to the software. We'll just kind of dive right in. Uh-oh. There we go. We're going to look at a generator. This is a turbine generator system. It's been in a couple of my webinars before. This one it looks across the coupling. So I have a coupling guard on. Unfortunately, they wouldn't let me take that off. I wanted to be able to see how the coupling was moving, which would have been pretty cool for this. I heard something. Mark, you back?
Yeah, can you guys hear me?
Well, I couldn't hear you before. You cut out.
Sorry about that. I don't know what happened there.
That's okay.
Yeah, just a couple of housekeeping notes. But before we get going here, I just wanted to let everybody know that this this webinar is being recorded. So you will get an email link after this afternoon or so after processes, and we'll send out the recording to the webinar. If you do have any questions during the webinar, you can go ahead and type those in the questions box in the GoToWebinar little panel on the right-hand side there. and we'll get those questions answered for you at the tail end of the webinar. All right,
might need to edit out some dead space in there when we lost you.
Sorry about that.
Technical difficulties. Okay, so we're going to look at the generator analysis here, and one of the things I want to look at is what's happening across the coupling. I really would have loved to look at the coupling itself and saw those motions, but there is going to be some shaft distortion in here that we will talk about, and there's a couple different ways we can look phase-wise and orbit-wise and what have you, vector-wise across this coupling to see what they're doing. Are they in phase, or what is the motion like? And it also includes some piping in here. Most of this is hardwired in. We're going to take a look at some of the piping issues and how to monitor those a little bit differently. And some of this is live, and some of it's going to be just animations that I've already made. And I'm going to walk through the animations first, and then I'm going to go live and show you a few things live in the software. First of all, the setup wizard has multiple steps. You might have seen this before. We select the video. We put in the frames and duration length we want. We set a distance so we can scale the time waveforms appropriately. We select a point density, and then we look at that point density and we filter out background noise and in the animation and really high amplitude stuff like this shaft distortion that we'll see in a moment. You have a video file that's set up there, the dimensions, the capture rate, which is very important. You have to throw that in, or else the slides will be screwed up. We captured at 1,057 frames per second. That gives us the maximum resolution on the image. The frame count for this was 8 seconds. And you might have missed one of my earlier webinars, the 8 seconds fills the buffer. There's in the Chronos camera, there's an 8-second buffer in there, and once it fills those 8 seconds, it starts over again and overwrites them. The reason that's important is because of camera jitter. And I've had several cases where the camera was still had a transient put into it because of my big chubby fingers, and it rang the camera support, the tripod, and it wiggled it for a while before it died out. This feature, if you fill that buffer a couple of times, so maybe take 20 seconds worth of data, you get rid of all that jitter issue. Okay, we're going to move on from here. Here I have my 1,057 frames that is hardwired in. I have 8 seconds from the start to end, exactly 8 seconds, so I get 1 second averages if I want to do averaging. I set the distance. This is a known distance, and it's 5 inches almost exactly. So I put that in, either drawing a horizontal or vertical line of known distance, put that in the distance indicator there, and we move on. We hit next. This describes a point density. So in the software, it's 1024 by 1280. If you multiply those two numbers together, it's something like 1.3 million pixels. We're not going to use all the pixels. We do an analysis to grab all the pixel information, but in preparation for animation, we're going to use something less than that. So we're using 26,000 grid points, and the grid points you can see on the screen. And if you get any more than that, you can't see the image anymore. And so they are very close together. They're nothing as close together as the pixels, but we're going to interpolate all that motion from the closest pixels into the grid work and get our animation there, something that the eye can see. Okay, we extract all the time waveforms and we get something like this. Okay, and you can see what really is happening in the shaft in the time waveform. So I have a raw time waveform, and then I have what's called a band limited time waveform animation. And I've put my bandpass filter around 1 times RPM. So this is still time domain. I go in, I put my band cursor on there, I save that information, everything else in the entire frequency range goes away, and I do an inverse FFT to get back to the time domain. And now I have an isolated time domain measurement at 1 times RPM. The raw time waveform animation on the left has all the frequencies in it. The band time limited one on the right has only 1 times RPM. So you can see it's a little cleaner. There's no jitter in it. That distortion that you see on the shaft is pretty pronounced. And in a lot of the time waveforms I'll show you when we go live, it's like a pulse. And that's the biggest vibration in the machine. And it's not really a vibration, it's just the passing of a piece of reflective tape, but it looks like a pulse in the video. Cleans up quite a bit when you get rid of all that other noise, that distortion. So mostly an axial and vertical bounce of this bearing housing. The frequency domain animation is something we get by just going into the FFT and putting our cursor on the whatever peak we're interested in, and it'll isolate that peak. I have 2 methods here. One of them is from the just traditionally from the Fourier spectrum. On the left, you put your cursor on the 1 times RPM and you get the same motion that you just saw up here on the right at 1 times RPM. This is the same thing in the frequency domain, but in the frequency domain, we don't have rotation of the shaft, or we can't make it do that. So what we were left with is a little bit of distortion there with that tape when it went around. Okay, this is the ODSFRF frequency domain animation, and it looks a little cleaner. The shaft cleaned up a little bit in between there. It captures all that phase information in the real, the imaginary, the magnitude and phase. So you can do Bode plots of all your data if you wish. This is something that we've been working on in the animations. It's just a point selection and not a big deal, but it'll give you as many points as you're interested in. I took selected a point on the top of the bearing housing on the bottom so I can see how they're moving on the bearing housing here next to the shaft, and then on the other side on the gearbox in the same location and direction. And then I threw in a spot on this this valve, what do you call it, meter. If you look, it'll give you the phase indications, and since it's a biaxial measurement, X and Y are always 90 degrees apart, but from point to point, they'll tell you slightly different stories as you move on, okay? These are all pretty much in phase with each other, just because the whole image is moving in the axial and vertical direction. This is the ODSFRF frequency domain orbit plot. Now this orbit plot gives you a little more information. It's kind of like the vector plot, but it's X and Y, so you're going to build an orbit every time you want to look at it. I took the top of the bearing housing and I can compare it directly to the bottom part of the housing. There's mostly vertical motion here. And as I get farther out by the bearing, it's got an axial component. Here, across the coupling on the bearing housing, it's mostly axial with a little bit of vertical. So you have roughly a 90-degree phase shift between the bearing housing and for the generator and the gearbox bearing housing. Okay, and then on my valve, I got another orbit-looking plot there. So we can label everything. We can select any points on the structure we want. We can do vector plots. We can do orbit plots. We can get amplitude and phase information, and everything is describable. There was one thing that I'm going to show you when we go live. Somebody asked me about, before the seminar started, about this vector plot that RDI apparently has. And the vector plot is along a beam, and there's arrows basically pointing up and down. Not realistic of a real machine problem, but they were wondering if we had something similar, and that is the orbit plot. And I know that they also have an orbit plot, but this is an XY system. If I excited this pipe in just this direction, I would see a vertical vector plot basically similar to what they're talking about. So maybe that question will come up again. I don't know if I've answered it properly, but hopefully I will. Well, let's go live then. Okay, if I get out of this and get into my MEscope, this is the animation, and you can see a little distortion. I can change the amplitude a little bit. Everything's kind of moving a little clunky. The reason it's like that is because of that distortion on the reflective tape. Oops, for some reason, can't, oh, there it is, okay. Sorry, it's behind, I have something you can't see on the screen. There, I'll move it out of the way. There we go. There we go. If I look all the way through here, this is these are sorted based on the highest vibration that you see. And I mentioned earlier that reflective tape going around looks like the highest vibration. It gives you a pulse every revolution, which is kind of annoying, but that's what it is. If I go down into any other part of this machine, or the image, it's sinusoidal. Okay, and it is in the time waveform, so there are 100% of the frequency content is in there, 100% of the phase content. It is moving all synchronized in one because all the data was captured simultaneously in the 1.3 million pixels. There is also an FFT response. So the FFT here is this band. If I click over here in the time domain or in the frequency domain, change my scale a little bit. Let me go here. And now I have an animation of the bearing housing in the frequency domain, just looking at 1 times RPM. Okay. So time domain, you get a little clunkier looking response because there's all the frequencies it's trying to accommodate. Plus I have this big distortion in the shaft, which makes everything look a little funny. Over here in the frequency domain, it cleans up a lot of that because I'm only animating 1 times RPM. Here's 2 times, a little bit of shaft motion, and I can rescale this a little bit. You can see that bearing housing bounces a little bit, but all the vibration, or a big portion of it, is in the 1 times RPM. And I can look at any of these frequency bins that I want, and this goes up to 30,000 CPM, so 530 hertz or so. Okay, go back down to there. Okay, now we can play a little bit. Up here are the hotkeys. So these are the features that we're putting in, and we're not quite hardwired. We're getting ready to do that next week, but we have a restart key. We set up band limiting. We can band limit the waveforms. We can calculate the ODSFRFs. We can animate from the ODSFRFs. We can animate from the frequency FFTs, the Fourier spectrum. And we can select points so that we can look at mag phase and we can look at orbits. Okay, so let me take a look at that real quick. We'll hit the restart button and it reformats everything. It gets me ready to animate, and it starts animating in the time domain. Okay. Number 2, set up, or number 1, set up band limiting. What this will do is it'll set up the frequency range around your peaks. It'll get the windows ready. It takes a few seconds here to get this going. Here it just copied the data, the time domain data into the FFT block. It's currently doing an FFT of all that. So here's my frequency response. And it should put the cursor back up when it's ready to go. And still going. There we go. So the band cursor's been set. We can acknowledge that. I don't like this because it's a little too wide for my taste. If I'm going to go in there and band pass something, I want it pretty close to the peak so I'm not getting any potential sidebands into the animation. So here's what I set the cursor to. They're just waiting for me to do that. Here's the band limiting time waveform command. We hit that, and what's going to happen here is I'm going to copy the FFT into my band limited waveform data block. It's going to show that range, and it's going to do a band pass where you get rid of everything else like it just did. And then it's going to perform an inverse FFT, and that's going to give me the 1 times RPM time waveform filtered. Okay, so we saw just earlier, I made some movies of it. This is the raw time waveform with all the distortions in it. This is the filtered time waveform from the band limiting routine we just did. Okay, and we can do that for any peak. Here's my 2 times. I go back up here and say, do the band limiting time waveform. It's going to copy that spectrum, and it's going to eliminate anything that's not in that band. So it's copying up into the potential waveform generator at the end. So here we are. It took everything out, does an inverse FFT, and you should have the time waveform from 2 times RPM. And there it is. And it'll start animating that. So this is a very subtle bouncing motion of the machine. And there was a problem with this machine in the foundation, and there was a lot of vertical vibration. And this doesn't seem like a lot. I can rescale it and make it look bad, but it was much bigger on the floor than we would have wanted, much higher. Let's see. All right, so the next one is set up band limiting, do the band limiting, set up, calculate the ODSFRF, and this will take a couple moments. Do you want to proceed? So doing an ODSFRF, we have all the time waveforms, something like 14,000 time waveforms, and what we're doing is doing the cross power calculation between one time waveform that's a reference and one and everything else that's roving, basically. Reference point number 1 is not the one I want. I want to be able to select it. So it says press hotkey 6 to select it. I do that, and I'm going to do it, let's do it here. Okay, so that's my reference point that I'm comparing everything else to. And calculate ODSFRFs. 1745, do you want to proceed? Yes. So 1745, when it starts to build it, here's 1745X. That's my time waveform reference. And this will crank a little bit, and then it'll go back and give me the ODSFRF. Oh, there's my transform. So this first pass through the transform, a little slow. I have virtually no space left on my computer. I do have a lot of nice videos though. And hopefully this will get going. All right, dead time is horrible. So we're going to, oh, no, there it goes, there it goes. I'm sorry for the delay. Something happened at 12% that it didn't like. All right, what else can I say? So the time waveform has all the phase information in it. What we're trying to do is be able to look at a frequency representation and use all the time waveform data phase information in the ODSFRF format. And that'll help us understand the vibration a little bit better. Whenever I'm looking at troubleshooting machinery, the time waveform is not nearly as important as the frequency spectrum. You get all your correct amplitude information. You get you can look at the phase if you wish, and it's the prescribed animation source that you'd want to use. Wow. It was working before we started today. I went through it all and it went faster. There we go. Okay, so now it's differentiating the spectrum to turn it into velocity. Come on. All right, there we go. So there's my ODSFRF. There's 14,000 ODSFRF files. Have all my reference information, and there's the animation. Okay. So I can animate from the ODSFRF. I can put my cursor wherever I want, and just like what you do from a traditional ODS with accelerometers. Animate from the FFTs. We can go back to that if we wish. We still have all these data blocks open. So I have a time waveform data block, I have a band limited waveform, I have an FFT, and I have a ODSFRF. So a bunch of animation sources that we can use. Now I'm going to select a point, and I'm going to do some labeling. So I want to know what this bearing housing is doing. I want to know what this lip around my shaft is doing, top to bottom and left to right, see if I have a cocked bearing or something in there. Here's my gearbox housing, and I'll put some references on there. And then my gauge. I like having my gauge. So this gets a little busy, but gives you a lot of information. So here's all my labels, and it's actually moving. And you can see all the different points that I took. This up here. I'm going to move these off the screen. So there we go. So the animation's telling us everything's pretty much in phase. There's an axial vibration, there's a vertical vibration. I get phase plots here, so I can look at this location, and you can see my X direction is in line with the shaft, or the axial direction. Over here at the top of the bearing block, I'm in phase. So those measurements from here to here, that point to that point, are in phase with each other. Okay, as you can see. Okay, it gets a little more complicated on more troublesome equipment. This generator coupling was actually working pretty well. Now, the one I want to do next is the orbits. Okay, error point must be selected before using. So I have to go to 6, select my points, and I'll do bearing housings. I'll do these two, just repeat what we just did, and top and bottom and one side of that. And let's go ahead and do it. There's my orbit plot. And I can rescale these however I like, but they'll all be scaled properly so that one isn't more than the other. And right now, this is my 1 times RPM cursor that I'm looking at. I'll zoom in a little bit more. And everything looks pretty much in phase. The only discrepancy is, you can see it here, there's a little more vertical than axial. And these are kind of 45 degrees or so. There's a vertical here. So my dominant motion on this is more a vertical bounce. Over here, it's axial. So all these orbits are just about as much axial as vertical, but a little more axial. Now, the question that came up before the seminar was, do you have some kind of vector plot you can use? And yes, we do. Let me get this going again. back and restart. Okay, there is a color contour, as you imagine, so we can see a little better indication of what's going on in the machine, and we can scale it however we like. There's also an arrow or a vector plot. In this case, I have a ridiculous amount of vectors, so it's kind of hard to see the motion. I can put the color on at the same time and so forth. So I need a little less resolution to be able to use this, where I'd like to see where the vectors are going. But the orbits turn out real nice. Let me turn this off. Okay, so I have my machine here. I'm going to go in and select the points again for the orbit analysis, but I'm going to do it, instead of along a beam, I'm going to do a pipe. I want to see how this thing moves all the way across the board. So I go right to the valve, go along the meter. So we'll see what we have here. Okay, so I've selected a series of points along the pipe. I can do my orbit plot. I can tell it to do a vector plot, but there's motion in two planes. And I don't want the time waveform, I want the 1 times. So this is what the vector plot would look like if it was in 2 planes. It's going to be an orbit. So I'm viewing this in the XY plane, and I'm seeing that motion. Okay, so everything's in phase, kind of moving with the bearing housing, and it makes sense. It's all hardwired in. If I come over here and look at the 2 times response, there's a little distortion because I took it right here where the shaft wiggles going by, but there is more vertical motion in this. Everything's moving vertically, not very high amplitude, but you can see how it is. So little distortions. There's not a lot of pipe motion, but it's a way to look at piping vibration and get a better idea if it's flexing or what have you. Okay, I think I'm good there. I'm going to go back to the webinar. Okay, this is the second part. This is a disk drive from a computer. Every once in a while, I get a new computer and I like to take the old one apart. If you've never done this before, there's the memory disk here. And a lot of them are solid state drives now, so you don't see this, but these are the reader heads. So they can move back and forth and change their diameter, and it writes with magnetic coding all the information in your computer. This looks like 4, that's a reflection. There's 2 on top. There's 2 heads that are in the mirror image at the top of this. This is all polished silver. Okay. So we're going to take a look at this drive, and we're going to look at it from a little different perspective. I wanted to do a natural frequency test on it to see what I could see, and I didn't have a tiny hammer. My hammer was something else, and I'll show you that in a second. We're going to grab this video. So I took about 5 seconds worth of data. We're going to set it up the same way we did before. It's a kind of a dark image, so I put some contrast on and I cropped it down. We have so many frames, and I skewed these so there would be no transit at the beginning or the end. And I took 4 seconds worth of data. It's still 1,057 frames per minute or per second. If I go to next, it's asking for a dimension, and this disk is 4.7 inches across exactly. So I should get a really good response as far as all the time waveforms being scaled properly. We put in how many points we want, and I just went with the maximum, 24,702. That's the biggest grid I can have for this. And what you get is a histogram where you can pull out the really high amplitude, low number of event occurrences like flicker and shininess and things like that. And on this end, you can pull out background noise, which would be anything that's outside the disk drive area. And I'll show you what that looks like. This is where I pulled off a little bit of the last bin stuff, but not much, and a couple of the first bin stuff. So I got rid of some of the background noise here. This was sitting on a table, this disk drive, and behind it was a white wall. So this is a mirror finish on this disk. So the wall looked like the disk right in that area. What I'm really trying to do is capture this ring, because I want to see if I can see the mode shape of this after I ring it like a bell. Okay. Normally you have a little hammer and you hit it like a bell and you get the bending modes, the flexural modes of that disk. You also get, as shown here, rigid body modes. So when I hit it vertically, the whole thing kind of bounced. So there's a little bit of flexibility in the table, and it's very small amplitude vibration displacement. And a couple of things happen. You know, it bounced up and down. Everything's moving in phase, and you can. That's verified by this. I have the right number of pixels to grab this whole edge without losing any definition. That's what I'm after. And there's something weird that happened. Apparently, when I hit this thing, I put a little torsional response into it, so it rotated. And it looks like it's rotating back and forth. That's not really happening. It's rotating in one direction, and then it does the next cycle. So you're constantly repeating that wiggle. This is me hitting it with a Sharpie. So it just touched the disk, and 1057 frames per second is quite a bit. So it takes a little while for the marker to get out of the way. What's happening during that time? There was a reflection of the marker right here. There's a reflection here from the moving disk. The light is just flickering a little bit. So not a whole lot you can do about it. So if I take my data right from now, I can amplify this and see what that peak is, or what the natural frequency is. The problem with doing something without a calibrated hammer or some method of striking it, I was on the disk for too long. So when you're doing a normal modal analysis, you hit and you ring it with a hammer, the hammer bounces off, and you only want to hit it once. If you hit it twice, it'll distort your data. This, I did okay, but it just obviously wasn't the right tool. The other thing I did was it was too big and I hit it too hard. I didn't give it a nice, clean little light touch. I held it on surface a little bit too long. So I got a lot of rigid body motion, okay, force vibration instead of a ringing response vibration. This is a close-up of that, and you hit it and you can see it flexing in side to side. So it's when this side's going down, that side's going up, and the reflection's kind of helping us see that because the reader heads aren't moving at all, just the disk. Okay, so the optical flow just saw this marker, or this Sharpie, coming in and out of view. It also saw its reflection and made a distortion down here. And so it's not a perfect science, but it's a good way to look at things and at least verify a frequency. This is the time domain. So the time domain for this, it rings down. This was in the middle of my 4-second window, and it was a pulse, and it lasted 0.2 of a second, basically, from 1.7 to 1.9. I ended up bandpass filtering this so that everything beyond 1.9 and below 1.7 goes away, and I have my transient ring down. There's also some DC shift back here from me hitting it, but this is the real ringing that I'm after. This is the high frequency stuff that is the higher mode that I'm looking for. This is once I did this, I like a normal ODSFRF or a modal test with FRFs, I did the FFT of that, and I have several modes, and they're all real complex. This is the mode I was after. Some of these are rigid body modes, structure moving and twisting and what have you. This is a 427 hertz. This is the first nodal diameter mode of the machine. I have a little line here. When this side's up, that side's down. When I put color contour on it, there's a lot of color here because of the shininess and the distortion. That is the biggest vibration when you're looking at it. And I can see the ring around here. So there's some yellow that's showing up here at the same time it's showing up over here. So difficult structure to do a modal test on. It would have been easier if I had I was going to say accelerometer, but they're usually too massive. You could also do this with a microphone. So you could hit it with something and capture the response of the microphone. And if you did that in enough locations, you could get a mode shape out of it. This is something else I did. So we have that orbit plot, and I was thinking, well, I should see, or I could do a vector plot, which turns out to be an orbit plot when you have XY data. I should be able to see the mode shape if I take points around the edge, and I can see what it looks like. And I can envision something. There was possibly a second nodal diameter mode in there, but it's a little crude. I really need to go back again and be a little more anal about how I took my data and took the video. But it is an interesting plot. Let's see how much time I have. I got a few minutes here. Oh, you know what? I'm not going to go live on this. I think I showed you what I wanted to from this plot. The only difference was having me walk through and do some of the tedious stuff that takes a little time. So let's not worry about that. I have some features that I want to talk about. And I don't do this enough. When we do these webinars, I'm more concerned about finding new things to play with and having, nice case histories and things like that. But we did go through a lot of features here. So we do have image filtering. There is a flicker suppression from your LED lights. And I've mentioned in other webinars, the first lights I bought, LEDs, I went to Home Depot and got a brand of them that's fine for if you want to work on your car or something. But if you do high-speed photography, it looks like you have a strobe light on. It is there. I never knew that LEDs flickered, but they do. So if you are out there and you don't have LEDs lighting yet, you need to get the dimmable non-flicker LEDs. They're probably the best ones you can get. It also has, we talked about the histogram that is generated once you go through all your data, where you can have low amplitude background noise suppression. That's part of the wizard. And you can have high amplitude background noise suppression. We can also rotate the image. One of the nice features, if I had to turn my camera on its side, I could also turn the image in the software. We can show shaft rotation in the time waveform animations. There's some little magic there. You have all the information for rotation in the time waveform. Sometimes it's distorted, but other times it shows up really well. We have some camera buffering options, and I mentioned it has an 8-second buffer in there with a manual trigger that you can buy, and it clicks onto the BNC cable here, BNC output. So if you touch the button on your camera, and I found this out the hard way, I'm putting a little bit of vibration into the tripod, and it shakes the whole thing slightly. And unless I get rid of that transient data out of the buffer, it'll show up in the video, and the whole frame will move around. So the best way to do that is to set it to an 8-second buffer and take 20 seconds or so worth of data so that you overwrite enough that it's got a good clean data capture. You don't have to use all 8 seconds. That might take a while to process. You can use a second of it, but at least you'll know that it has good data in it. And the manual trigger helps you turn it off without touching the camera. This is the camera that MEscope Vibrant Technology was recommending, and we still are. There's a couple versions of it, and it turns out to be a pretty popular camera. They sell a lot. They've been selling these like crazy. Signal processing wise, operating deflection shape from video time waveforms. We can do experimental modal analysis from video time waveforms. My version of that today was real good, except it was not applied properly. If I took my data a little bit better, I would have got better results. One of the things that also will occur in something like that, the disk that's vibrating has natural frequency modes much higher than 500 hertz. So I could maybe reduce my resolution and double the frequency response, and I'd be able to see if there's peaks out there that might be worth pursuing. We can do time waveform animation, frequency domain animation, and ODSFRF transformation animation. So there's a lot of sources. In the example I showed, we had 4 different time block animation sources, which is pretty common for covering all your bases. The software itself, FFT and inverse FFT transformations, there's low pass, high pass, and band pass filtering, and there's frequency band extraction. So you can set up those filters properly. You can pull out a 1 times, a 2 times, a 5 times, what have you, and get just that frequency in the animation. There's also integration and differentiation. The data we are taking is displacement. So instead of using an accelerometer and going to velocity where you'd integrate, using this in displacement and going to velocity, you have to differentiate. Okay. There's interpolation processing inside the software, so we can re-interpolate if we desire later on if we're modifying our data, cleaning some things up. There is FFT averaging, and we talk an awful lot about the image and how the image is moving and what to look for and things like that. The FFT averaging does the same thing for your spectrum. Okay, for your ODSFRF, if you take 8 averages, it has an incredible amount of noise floor reduction, and it really makes your data look good. Especially if you got noisy data, it'll pull peaks out of the noise floor. We have live cursor amplitude and phase, live cursor orbit analysis like we just showed you, and there's examples of that right here. We have presentation-wide, we have normal exposure images where it's, I wouldn't say black and white, it's a color camera, so it takes advantage of that feature. We have color contour imaging options. This places a window in front of our piece of machinery, and we can color code it to the motion. So in this case, I had some rocking motion from a softwood or a delaminated plate in my motor house foundation. We also have intensity vector imaging, which is this. So I have a grid here, and I turned on the vectors, and I can see the changes in motion, both in color and with the vectors changing direction and stretching. So it adds a little feature that's good to see. We can label and create orbits at any grid point. So we've got lots of different ways to view the data. Now, what might you want to know about the pricing? The one thing to know is if you already have MEscope software, if the software gets a lot cheaper. We're going to start from scratch in the first package. We need a camera and a camera lighting kit that goes for about $6,400. We're going to need MEscope Visual Pro ODS software, $75.95. We need the VES 9000, which is the video software. Okay, so all that together, it's under 20 grand, which is a incredibly good cost. But if you already own just basic ODS software, you need a camera, you need to upgrade the signal processing, and you need to get your video software. So you're down to 15.4. If you already own 420, which is ODS Pro software or better, you just have to buy a camera and the video software. And if you already have MEscope that's higher than Visual ODS Pro, and you already have camera and lighting, it's $6,000 for the video software. So it's pretty cheap, pretty inexpensive method of doing a whole lot. It's a big powerhouse. And the folks at Vibrant Technology, they're releasing a software version every week. They upgrade it, they take out bugs, they find new things. I'm constantly bugging them that why can't it do this or that, and they respond. And it's really a great place to work. The other thing, there is a discount. What was that discount, Mark?
Yeah, if you reference the code ODS10 when you either call into our sales or if you're working with a local MEscope reseller, just reference ODS10 and you'll get 10% off your software purchase. And
that makes it even better.
There you go.
And last of all, training. There is training. There's a couple types. Now, when you do this, you want video training, which we can do. That's not a problem. But we also offer ODSFRF training, which is the traditional accelerometer-based training. And what you get in that is the workbook where you'll go through 12 or so completely written out projects, step by step. Everything's right there, and you just follow the directions. You get used to the format where everything is, and in a short period of time, you're making models, and it shows you how to do that. So that's an option as well. 2 days of on-site or regional training, USA or Canada, it's $5,000 for up to 2 students. Additional training days by the customer request. If you want to do a little bit better, you want to build ODS models and things of that sort, it's $2,500 per day extra. Any additional students are $1,000 per student, so it's pretty cheap, inexpensive training program. Includes course notes, project workbooks, 14-day software license, the whole bit. So you don't have to buy it yet. You could still do the training, which is going to be useful down the road anyway. But you'll get this 14-day software license where you can learn what you need to know before you decide on what to buy. And there's that. I'm done. What do you think, Mark?
Looks good. We had a couple questions.
Okay.
Let me pull these up here real quick. First question is, can ODS work on moving objects? Your examples show this technique works well for stationary objects bolted to the ground. However, Amazon's robots pick up tall shelves, accelerates and decelerates them, and it's critical to determine or visualize what the sway displacement is. So, yeah, question about, can we use this on moving objects?
I assume you can. I'm trying to figure out how that would look. The animation, the high-speed camera will slow it down. So you're going to be able to see things in the high-speed exposure. It depends on, is it coming to a stop where, you go to, it's a robot and it's going to its extreme and stopping and changing direction, or it pauses for a moment. That's an area where you can see it have a big transient that you normally wouldn't see. So you can see how it loads when it comes to a stop or starts up, actually. And it'd be a short video, but trying to think how you could do this. You'd get vectors all the way through, and I assume that the vectors would be some kind of stretching arrow or arc. I'm sure it can be done. I don't have any experience doing it, but it seems feasible. I'm not sure the limits of the, not the software, but the algorithm.
Mm-hmm.
The optical.
David, we'll get back to you on that one. I can get some more information from some of our engineers and follow up with you on that to get you a clear answer. Another question from, let's see, from Gary Williamson. Can you choose a few points and vector just those? I think we demonstrated that. But
like I, vector them. Well, I did orbits. I tried to do that.
Orbits, but
yes. Well, same thing. If it was piping, I could do that. If I was looking straight onto a pipe, I was just thinking, well, how can I do this differently and not have orbits? I would suppress the either Y or X direction. So I'd take a horizontal view of a pipe or a vertical view, and I would cancel out one of the directional vectors, and then I could see, bending modes of the pipe. Shouldn't be too hard to see. You just have to, shouldn't be too hard to do. You just have to know which direction you want to suppress.
And I believe you've demonstrated that in a previous webinar too.
Yeah, I probably have.
Yeah. So incidentally, all the webinars that we, all these ODS webinars that we've been doing here for the past couple months, they're all available up on our website. So you can take a look at some of the past recordings, including this one. We'll go ahead and put that up on our website here and probably be up there first part of next week. Second question from Tom, technical question. What settings define the frequency range of the FFTs?
The resolution and the frame rate. So the frame rate sets pretty much everything. That'll tell you what the resolution is going to be. That 1048 by 1280, whatever that grid was, that's the best resolution you can get for this camera. And that turns out to be a frame rate of 1057 frames per second. If you want to go higher in frequency, you can speed up the frame rate, but you start to lose resolution. Right now, this camera at 1057, you have your Nyquist frequency, so you really only get half of that in the frequency range. So instead of frequencies per or cycles per second, you get frames per second, and your Nyquist frequency would be, or factor would be 2, so you'd get 1/2 of that. So we get about 538 hertz frequency range. Somebody else from other webinars, they talked about aliasing problems as well, signal processing problems. There's no way to stop aliasing, but you can identify them. If you just doubled your frame rate and went higher in frequency, now you'd be up around 1,000 hertz, and you could see if there's any dominant peaks out there. And if there are, they potentially could corrupt your data if you don't know what they are. That's another can of worms, but there is a way to do it too.
Gilberto has, he says, damn, fantastic tool. Congrats for the presentation. So thank you, Gilberto. That's very nice of you. He's got a couple of follow-ups to the question regarding the moving objects. We do have a request from Fiat. They want to understand the stick and slip vibration of windshield wipers. We've tried to use laser vibrometry near the wiper axle, but it was hard. Looking at the wiper as it moves would be great. So yeah, I think we need to do some testing on that on our end. Yeah. So certainly we'll, and that might be a great lead into our next webinar. So we can look into that.
I agree. I think the slow motion, effectively slow motion video from the high-speed photography would be really nice to have.
Yeah. So
and then extracting the time waveforms from that. I think it has to be a transient condition where you're either starting or stopping that wiper blade. That's where you're generating the big acceleration and a big transient pulse.
Yeah. Okay, just a few others that were commenting. What a wonderful presentation. So thank you all for joining us. That's it for the questions right now. If you do have some additional questions, you feel free to email those at webinar@vibetech.com. Again, webinar@vibetech.com, and we can go ahead and get those questions answered for you. And just want to remind you again about the promotional code. If you reference ODS10, you'll get 10% off your purchase of the software. So either you can reach out directly to us, you can reach out to Dan, or you can talk to your local MEscope reseller. With that, I think we'll go ahead and wrap it up. And like I said, well, I'll get this, you'll get a link in your email to recording of this webinar. So keep on the keep a lookout for that. And we'll have another webinar queued up for you here in a couple weeks. So keep an eye out for the next invitation. Anything else,
guys. Dan? No, thanks for coming. Appreciate your attendance.
Appreciate it. Thank you, everybody. Have a great weekend.